Some time ago, I was asked to be a judge at a local school science fair. I went to the school to do my judging duty, and there were the usual projects. Elena had a volcano that erupted a vinegar and baking soda mixture. Philip displayed a three-dimensional mobile of the solar system. And Mariah discussed a potato in a jar of water with a plant growing out of it. But I was looking for something more. Was there a kid there that really wanted to conduct a scientific investigation? Then I found it. Back in the corner of the gym was a small table and an even smaller boy with a rather crudely made poster. It read, "How does the angle of a ramp affect how fast a toy car will roll down?" I quickly made my way over to the boy's station and saw that he had an experimental setup with a long wooden ramp and a way to measure the angle of the ramp. He also had a toy car and a stopwatch. Perfect. Intrigued, I asked him a number of questions. What is your hypothesis? How would you describe your experimental setup? What were your results? Did they support your hypothesis? What about errors in your measurements? Calmly, the boy answered each question and then showed me this table with results scrawled in. After a long discussion with the lad, I came to the conclusion that he had conducted a thorough scientific investigation and had learned much from this experience. I voted for an A grade. Let's find out more about what constitutes good scientific investigation. Scientific investigation is a quest to find the answer to a question using the scientific method. In turn, the scientific method is a systematic process that involves using measurable observations to formulate, test, or modify a hypothesis. Finally, a hypothesis is a proposed explanation for some observed phenomenon based on experience or research. Scientific investigation is what people like you and me use to develop better models and explanations for the world around them. As you can imagine, there are several phases to a good scientific investigation. These may vary a bit in the literature, but they generally include 5 steps. Step 1. Observe something of interest. The young man at the science fair obviously enjoyed playing with toy cars and had noticed that when he increased the pitch of the ramp, the cars went faster. He wondered what the relationship was between the steepness of the ramp and the speed of the car, beyond just the obvious fact that it went faster as the slope increased. People who engage in scientific investigation usually do so because they don't know or are unsure of some aspects of the observation, or because they want to confirm a hunch about the observation. Step 2. Formulate a question that can be answered in a measurable way. It's important to ask the question so that it can be answered in a measurable way. Beginning with the question with what, how, or why is a good start. The question should also be focused. Many researchers make the mistake of trying to boil the ocean with a question that is too general. For example, why do people get sick would not lend itself to a good scientific investigation in anyone's lifetime, even though it's a pertinent question. Remember, boiling the ocean is quite a bit more difficult than boiling a pot of water. Step 3. Formulate a hypothesis that answers the question based on experience or research. You may be wondering, why come up with a hypothesis about something we're trying to discover? It's much easier to analyze data and compare it to an existing theory than to try to develop a theory from scratch. There are already good models for much of what we observe, so we can usually find the seeds of an answer to our question through research. Many times, scientific investigation is used just to make incremental improvements to a theory, process, or product. In short, the hypothesis brings to bear all that is already known about the question. It gives us context for what we're studying. When I asked the young boy about his hypothesis, he said, "When I play with my cars, I notice that when I start increasing the slope of the ramp, the speed of the car seems to change a lot. Later on, at the higher slopes, the car goes fast, but each change seems to have less effect." My dad's a teacher, and when I talked to him about this, he said that the force of gravity goes straight down. So the part of gravity that is affecting my car changes with the angle, but it changes less at the higher angles. He said it has something to do with trigonometry. I don't know what that is. Anyway, that's what I am expecting to happen. Step 4. Set up an experiment from which data can be gathered to test the hypothesis. This is the fun part, but it is also the easiest step to mess up. Experiments are fraught with uncontrollable variables, bias, measurement error, and other unintended consequences. So it's important to understand all these things and take them into account as much as possible. Here is just a short list of all the variables and potential errors affecting the car and ramp experiment at the science fair. The boy I talked to was well aware of the fact that it was hard to measure the time the car took to roll down the ramp with a stopwatch. In fact, he said that when the angle got above 50 degrees, the stopwatch just kept giving him the same time, around 0.8 seconds. He decided that he really couldn't get accurate measurements for higher angles than that. I agreed with him. We talked about the friction in the wheels of the car. He had thought about that, but wasn't sure how it would affect the experiment. Step 5. Analyze the data, draw conclusions, and confirm or modify the data. I asked the young scientist at the science fair if he had any graphs of the data. Sure enough, he realized that plotting his results would help him visualize what the measurements were telling him. Here is his plot of speed of the car versus the angles he measured, the orange dots. He had also added in a curve, the green dotted line, to approximate the points. Good thinking! Moving to the conclusion phase of the scientific method, I asked the young scientist at the fair, "Does this chart support your hypothesis?" He thought about it and then said, "It shows that the speed goes up as I increase the angle of the ramp, but it also shows that the speed levels out at higher angles, so yes, this is what I thought would happen." I congratulated him for his insight into something that, frankly, some of my college-level physics students still don't understand. Scientific investigation uses the scientific method to answer a question. The scientific method is a systematic process that includes 1. Making an observation, 2. Stating a question, 3. Formulating a hypothesis, 4. Conducting an experiment, and 5. Analyzing the data and drawing conclusions. The hypothesis is nothing more than a proposed answer to the question being asked. In the end, the goal is to either confirm the hypothesis or to modify it. Each step of the process must be handled with care. For example, the question should start with words like what, how, or why, should be focused, and should be something that can be answered in a measurable way. The hypothesis should be based on research or personal experience. Finally, the scientist should understand all of the errors due to measurement, bias, and uncontrollable variables that can affect the experiment. Scientific investigation, when applied correctly, will continue to be the main way that scientists build better models and explanations for phenomena in the world around us.